This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Howard Chu. Howard Chu has been writing free and open source software since the 1980s. His work has spanned a range of computing topics, including most of the GNU utilities, for example, GCC, GDB, GMake, etc., networking protocols and tools, kernel and file system drivers, and focused on maximizing the useful work from a system. Howard founded Symas Corporation with 5 other partners in 1999 and serves as its CTO. His current focus is database-oriented, covering the LDAP protocol, LMDB, and other non-relational database technologies. Howard, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
I think that covers it for now, yeah.
That's quite an extensive list. Cool. So today's show is on a pretty meaty topic called B+Tree Data Structures. And they keep coming up in other related software engineering radio shows. We touched on them in my first show that I did for Software Engineering Radio with you on LMDB. We did some in episode 454 with Thomas Richter on Postgres as an OLAP database. Simon Riggs on Postgres, episode 362, and Database Engines, episode 415. So someone has to try and tackle the topic, and I know you're an expert in it. So here we go.
Okay.
So I think because it's so complex, I'm going to split the show into 3 parts. We're going to dig into what tree algorithms are, B-trees, lay the foundation, move on to B-trees in a bit of depth and what's involved, and then probably halfway through the show, we should have enough laid down to tackle B+Trees. So here we go. I'd like to start with an overview of what a tree algorithm is, its terms and its history, so we can lay a good foundation. I'll then move us on to B-trees and finally on to B+Trees. So what do we need to understand first?
Well, all right. So these data structures are used to quickly search for items in a large data set. And the tree structure is used because it allows you to search more quickly than, for example, just a linear list layout.
And how would you describe a sort of tree algorithm? Is that where you can search things quickly, or?
Well, it's called a tree just because of the logical way the data is arranged. You start with a central root point, and then it branches out to different levels to cover the entire span of the data range.
So if you just to think about a regular tree in the ground, the root would be the trunk, and you turn it upside down and think of it from...
Yeah, so the computer science version of a tree is upside down from what you would see in nature, yes.
Okay, I'll keep that image in my head. So there's a few terms coming up that have a stab at, so we can try and break these up. So what's a binary search tree?
Okay, so that would be the most fundamental, the starting point for most of these tree designs. And it's based on a simple search algorithm where, let's go back to our flat list. Let's say you have a list of 100 items and you want to find one specific item in that list. The slow way to find it is to just start at the beginning of the list and check every element until you find the one you're looking for. And on average, it will take you 1/2 of the number of elements in the list to find the item you want. So if you've got 100 items, on average, it will take you 50 lookups to find what you're looking for. Okay? So we can improve that drastically using a binary search. In binary search, you take whatever list you have and you examine the element in the middle. All right? So if we've got our 50 items, if we have our 100 items, we look at the 50th item and see, is it the one we're looking for? And I forgot to mention that this only works if the list is in sorted order, right? So go to the halfway point, you find the 50th item, you see, is this what I want? If not, you see, say, is it higher or lower than what I want? If it's higher than what I want, then I go and divide the next interval down. So from the middle of the 50th, I go down to the 25th. Okay, so at each point, if I don't find what I'm looking for, I can either go higher or lower and divide the next interval in half. And so that's the essence of a binary search. And the way this improves things is at every step, you eliminate at least one half of the elements from consideration. So it'll get you to the one you're looking for much faster than a simple linear search.
Excellent. I think you've answered my question of why we need a tree algorithm and binary search tree. So is there a particular time you would use them, or a certain type of data, or does it matter?
It could be used with any kind of data. So the other thing that gets us to the tree structure. So first of all, what I described as binary search is how you execute it if you have a flat linear list, right? But you can basically encode all of those halvings and subdivisions by rearranging your flat list into a tree structure, right? So at the root of the tree, you put your 50th element, and then at the two children of that, you put on the left half, say you put the lower 50 items, and the right half you put the upper 50 items. And then at each level below that, you subdivide and keep on branching out. And the other thing to point out is, every element, every node in this binary tree has up to two children.
Yeah, I was just trying to visualize that. So if you imagine the root as a dot, and then you draw a triangle shape with the dot at the top and then two dots on the other side, join them together. That's your triangle, and they're the two leaves, two children, as it were. Yeah.
A bit
so
hard
just split.
to
So
describe
if you have the dot and draw a straight line down, at most you're going to split that into two, and then have two more dots, split them down again. So maybe visualize a deck of house of cards. When you're stacking cards.
Well, yeah, very similar, yes.
So you've got the two cards pointing together at the top with a one card base, and then every end of the card is another 2 points of a card, isn't it? If you're looking at that front on, you'd see the root structure and the 2 points.
Yeah, exactly.
Yeah, that's good. I just figured that on the spot.
That's a good analogy. So you're asking, why do we need them, or when do we use them?
Yeah, how and when is it used? When would you redo that?
The original, the generic binary tree that we just described, these days it's only used as a teaching tool to give you the idea of what you're trying to accomplish. In practice, a plain binary tree has a lot of management problems, so it really isn't used in real life. It's used in computer science classes to teach you about binary searches.
Okay, well, at least it helps us discuss the terms, which we've touched on. A root being the base of that tree or the top of the house of cards. A leaf, is that joining a root to the next node? To the next.
A leaf would be a bottommost, a terminal node, and anything between a root and a leaf is generally called a branch.
Okay, so is that enough foundation to understand what a B-tree is, do you think, or should we expand a bit?
That covers binary trees. So, as I alluded to, there are some problems when you work with just a plain binary tree, and that would lead us into discussing B-trees. Sure.
Would you want to touch on some of the problems? I know it's academic, but
yeah. Well, the first thing is, it's easy to construct a binary tree if all of your input data is already sorted when you begin. Okay. But if you have a very naive algorithm that says, for example, you start with a node of any particular value, and you want to insert the next node, and you could say, is the new node less than the current node, or is it greater than the current node? And if it's less, you make it the left child. And if it's greater, you make it the right child. If you actually start with a perfectly sorted input data set, then this very simple binary tree construction algorithm will actually give you a linear linked list, because every new node will always be either greater than, say you have a list that's sorted in ascending order, then every new node will always be greater than the one that preceded it. So every time you do an insert, you'll always insert onto the rightmost branch. And so you'll get a degenerate tree, which actually looks like a straight line, which is not very useful for the other search properties of the tree.
Yeah, because the left leaf is the lower side and the right leaf is the upper side. So if everything's higher than the previous one, then you're only going to be populating the right side, aren't you?
That's right. Yeah, you'll never populate the left side. So this is one of the problems with a plain binary tree, is that it's very easy to get into these degenerate forms that aren't balanced, right? And if it's not balanced, then you don't get any advantage of the binary search properties.
Yeah, where you split it in half and look at the higher or lower, because there's never a lower.
Exactly.
So you'd be better off just going back to the original way and counting.
Yeah. And so that's the most fundamental problem that motivated, the development of something like a B-tree.
And this isn't new, is it? It's been around.
Yeah, it's been around at least since the 1970s. Yeah, I think the first published paper is 1971 or 72.
Okay. Just before we move on to what Btree issues solve, can we just revisit a root, a leaf, and a node? Was that the right word? Root, leaf, and...
They're all nodes, right? There's a root node, there's a leaf node, and there are branch nodes in between.
Yeah. So a leaf is... Yeah, you describe it again. I won't get in the way.
All right. So the root is, the starting point, right? And the leaf is a terminal point. A leaf has no children. Okay,
that makes more sense.
It's the end of a line, right? And anything that is, interposed, anything that connects between the root and the leaf is a branch.
Okay, and a node can only have two branches.
In a binary tree, yes, a node can only have two branches.
Okay. And if it has no children, it's a leaf.
Yeah. A node can have up to two branches. It could have 0, it could have 1.
And that could be a right or a left, depending on whether the value is higher or lower. I think we had a good stab at covering the basics and the history there. So if we feel ready, let's move on to the main types of B-tree. So what is a balanced tree, if we could revisit that?
Okay, so, we mentioned that, if you just naively construct a binary tree and you have data of a particular arrangement, for example, sorted in ascending order, then you won't have a very good tree structure, right? It won't be balanced, and it won't give you any search advantages. So, this problem was recognized pretty early on, and people thought about ways to make the tree structure self-managing, self-balancing, so that as you insert data to it, it always manages to check its own status and rebalance things as necessary. And rebalancing in this case means actually changing the shape of the tree. For example, let's say I construct a tree with 3 nodes, right? And I'm just inserting the values 1, 2, and 3. And if I start naively by just saying I insert node 1, and then I insert node 2, and since 2 is greater than 1, I put it on the right child. And then I insert node 3, and 3 is greater than 2, so I put 3 as the right child of 2. Okay, so now I have a 3-node tree that's a straight line, right? And a rebalancing operation in this case would look at that tree and say, well, that's no good. We're going to rotate it left by 1 position so that node number 2 becomes the root. Then node number 1 becomes the left child, and node number 3 is still the right child of node 2. And then we have a perfectly balanced tree.
Yeah, I'm thinking of, might be totally irrelevant, but when you go to a website and they've got one of those, looks like a molecule structure, when your mouse hovers over it, it moves about. Kind of like one of those where you've started with the root as 1 and then 2, 3, so you've just dragged number 2 and put that at the top, and then you've got 1 below it and 3, reforming the tree structure. Yeah, I get that. That makes sense.
So what we just described is a balancing operation. And the idea is to, develop an algorithm that manages a tree structure so that it balances itself automatically, so that it can do the analysis that we just described and just automatically keep a tree balanced. And the Btree is actually only one of several ways that have come up, in computing to solve this problem, to solve the self-balancing problem. And two other ones that are very common, again, they're taught early on in computer science courses, is a red-black tree and an AVL tree. So
let me just chat about those two. Where we talk about an algorithm that rebalances the tree, some practical way of that might be there's an insert value, and part of that function looks to see what is there already and then makes some decisions and gives you an okay, but behind the scenes it's rejigged things. Is that how that sort of looks?
Behind the scenes it's rebalancing?
Yeah.
Yeah.
So you have an API that you're using to insert a child or a value, and then part of the algorithm and the library that you're using looks at everything behind the scenes and rearranges it, but gives you like a return value of 1 or okay or something.
Yeah, generally it's, for example, in the case of a Btree, it will attempt to do the insert first and then fix up anything that needs to be fixed up afterwards.
Okay, so it'll take the data as quick as possible and then...
I mean, the effect is the same because, the caller will have to wait for whatever cleanup or rebalancing to finish before the API returns.
Okay, just like a normal API. Okay. Since you mentioned those other two types of trees that you're familiar with, if you can give us a bit of information about them, that would be great.
Well, they're both improved versions of a binary tree. For example, in an AVL tree, first of all, we were talking about binary trees where we inserted a node with a simple value, right? Node with a value 1, a node with a value 2, and a node with a value 3. In an AVL tree, we add a little extra information to each node. We call it, a balance factor. So when you insert a value into a node or into the tree, it goes into a node, and the node starts off with a balance factor, say of 0, that means it's balanced. And if you add a left child to it, it might get a balance factor of -1 that says, okay, there's something on the left side. Or if you add a child on the right side, it might get a balance factor of +1, meaning that it's got a child on the right side. And the algorithm that maintains the tree will go up and down, examine these balance factors, and if the balance factor ever exceeds +1 or -1, like if the balance factor gets to 2 or it gets to -2, then it knows, oh, this tree is now too heavy on one side, and it'll know that it needs to rebalance it. That's the basic idea behind an AVL tree.
And is that attribute value something? What does the AVL stand for?
As I recall, they were the initials of the people who invented it.
Okay, so just a name.
Yeah, just a name. A red-black tree is actually named, they maintain balance factors as well, but they name them as colors, red and black. It's the same general idea.
Okay. What are array? Is it? How do I say this? Array search trees?
Okay. So far we've been talking about a binary search tree where every node can have 2 children, right? An M-array tree is where any node can have
that's just clicked.
n children. Right?
Sorry to interrupt. That's just clicked why it's a binary search tree, because there's only one of two values.
That's it. Yes.
This is more for me, this episode. Thank you.
Okay. So yeah, binary search tree is branch factor of 2. Any node can have up to 2 children, and an M-array tree is just the more generalized form where any node can have up to m children, where m is whatever arbitrary number that you want to assign it to.
But they have to be equal, don't they? They have to. All levels of the tree need to have up to that amount.
That's right. Yeah. We're going to start diverging soon from typical computer science teaching on this as we go a little further into this. But for now, okay, we're talking about Btrees and a fixed branching factor. Branch factor being the maximum number of children a particular node can have.
Yeah, we should probably just stick to Btrees. Okay. So I think we touched upon logarithmic and Big O notation in our first show together, and probably across quite a few other shows we've done on Software Engineering Radio. Would you just like to give a summary of that? Because that's what this all brings us, isn't it? That's how it's all measured.
Sure. Well, yeah, the Big O notation, basically, you'll see capital O and parentheses and some factor inside. And that means, semantically, it means on the order of, right? So if you say something is Big O of log n, that means the complexity of that function is on the order of a logarithmic value, a logarithm of the number of elements. So, if we look at our very first example of the linear search, in Big O notation, that's Big O of n, where the complexity of searching that element, searching that structure, is basically equal to the number of elements in the structure.
So it's a form of notation to let you know how fast or slow something's going to be.
Well, how complex something is, which usually means how fast or slow it is. Yeah. The larger the number, the slower it is. And so, the logarithm of n is always smaller than the value of n, and it increases much more slowly than n itself increases, right? And so that's a very desirable property in algorithm because it means the complexity grows very slowly. That means as data volumes increase, the performance decreases very slowly. Ideally, you would want the performance to not decrease at all, but that's not really
this
true.
is normally the graph that starts level and then curves up near the end, or the other way around. When you see it,
starts and curves up slowly.
Yeah, that's right. So Btree is a balanced tree. That's just a short way of saying, isn't it?
Yeah, it is one of the self-balancing binary trees.
Yeah.
Except it's not necessarily binary, right? It's m-array. It's an arbitrary factor.
Okay. And is there a proven statistic of how fast they are? If you follow that structure.
Well, it is a logarithmic algorithm. It's Big O of log n, and the base of the logarithm just depends on the branch factor. If you have a binary, if you have a B tree that has m equals 2, then it will be to the log of base 2. If you give it a branch factor of 4, then it'll be O of log to the base 4.
And how would you decide between a binary tree and instead of 2 nodes,
some larger factor?
Yeah.
So that's really a judgment call that needs to be tuned for the use case, because one thing you're trading off a couple of things here. The more branches, the more elements you can pack to a node, the more branches you can put to a node, the fewer nodes you need. Okay.
Yeah, that makes sense.
But the larger a node becomes, the more work it takes to maintain the pointers inside. So Like if I have a node that has 100 elements, that would be slower to manage than a node that only has 4 elements.
Yeah, and if you're doing, I think anyway, this is just how I'm understanding it. If you've got a binary tree and the node's just got 2 children, and the right leaf is the higher value on the left, but then if you go to 4 or 7 or whatever, you've got to then order all those in the right way, don't you, of each node?
Yeah, you have to keep all of them sorted, and you actually have to execute a binary search within that node to find what you're looking for.
Yeah, and you've got to keep that all in your head as you're thinking about it when you write the code.
Yeah. Generally, you're going to find, in textbook examples of a B-tree that, they'll pick some fixed number and never worry about it again. It'll be like, okay, we're going to do 8 nodes or 16 leaves per node or whatever, and then just forget about it. It's just set it and not worry again.
And is it something that you would come back and revisit at some point, or?
Well, we're talking about the general B tree here. When we get to B+ trees, those considerations go out the window. So
okay. So we've spoken about a B tree. We know we're going to move on to a B+ tree, but there's a B- tree. Can you tell us a bit about that?
Oh, no, B- tree is just another way of writing B tree. It's
maybe it's a typo of mine then. Okay, we've covered logarithmic time. So a B tree is well suited for storage systems that read and write relatively large blocks of data, such as disks. Do you agree with that?
I think that's more suitable for a B+ tree. A B tree, the general form of a B tree, it can be tailored for block storage, and the idea again is you make your nodes the same size as your disk blocks.
Okay, yeah. So this is the actual link of getting back to file systems and why it's used there.
Yes.
Okay, that makes sense. So if the block size, which nowadays is 496 kilobytes, isn't it?
4096 bytes, yeah.
Bytes, yeah. And that would be your biggest leaf node. What would that be?
That would be the size of your node, yeah.
Yeah.
In the B tree, all of your nodes should be the same size.
Okay, so let's start the big one. So just to recap, we've gone over a binary search tree. So that's a root node, and then children. Each leaf can have 2 children, left and the right. The right's generally the higher value, and the left is the lower. And everything's sort of founded upon that. We've moved on to balanced trees. So there's always a left and a right. We've discussed Big O and logarithmic time and the current uses for B trees. Now we're going to move on to B+ trees. Right, so let's start again. What is the B+ tree data structure used for today?
It finds a lot of use in all kinds of data management applications. For example, in many, say, SQL databases, relational databases, a B+ tree is almost always used for indexing. And in some cases, it's also used for the primary data tables.
And why is that?
Well, it's always used for indexing because, it is a structure. It's an ordered structure, right? So it's fast to look up elements in. Mm-hmm. And, it lets you move sequentially through the data set. So if you want to retrieve elements in a sorted order in a particular range, it's very well suited for that. For the primary data sets, it's not always used because, generally a B+ tree has range limits on the sizes of items you can put into it. So while you might have data with relatively small keys, say, 8-byte integer keys, if you're attaching, say, a 200 megabyte value to that key, it may not be so easy to manage in a B+Tree. And so you might use a different data structure to store the actual data that goes with the keys.
Okay. What relation? Say it was a simple key value store you're trying to implement. What relationship does the Btree data structure have to the key and the value? Is the node a key, or is the key just a bit of data in that tree?
Okay, so if we back up and look at what we talked about in Btrees, we actually were using a much more simplified example where a node only contained a single value, like an integer, right? 1, 2, or 3. So in that case, in the terms that you're talking about, it would be a key-only database.
Okay, yeah.
Because the only thing we were storing in there was a searchable value that was a key. In the case of the B+Tree, we have those keys, those numeric keys, but we can also associate with them an arbitrary blob of data. And in a B+Tree structure, only the leaves of the tree actually store the data values. All of the root and interior nodes will always store only the keys.
Okay, so the key coming in, for example, in a database search, would be part of a select, and because you've got an index created for where such and such equals something, then that's the key, so then you can reliably predict how quickly that's going to take. It's going to be fast. So you can see if you find an index which will then recover the value, which is the row where the information is stored.
Yeah. And again, if you're using a B+Tree only as an index, then the value that you get back is just going to be a pointer to the data that lives somewhere else. Right?
Yeah, I think I'm getting it now. Good.
Okay. And again, there's the alternative where you actually use the B+Tree to store the primary data as well. In that case, the value that you retrieve will be, the complete data item that was associated to that key.
Because if you've got a quick lookup in the index, you still want a quick way to find the actual data you're asking for as well. So you could potentially have the two B+Trees, like you just said. Yeah. Okay, we can move on to question 3. So what extent is adoption driven by some of the newish hardware, like SSDs or newer types of memory for this tree structure? Do they have to change it for where the blocks are stored or anything like that, or is that sort of transparent?
It's a lot of the answer to that question depends on what the operating system is doing with the different memory structures or the newer types of memory, as you were talking about. There's persistent memory or like Optane memory or some other things like that. You have the option of making that memory transparently usable, or you have the option of making it an explicit block device. So it really depends on what the operating system has done. One of the things that we didn't state explicitly here is that in the B+Tree, again, we're talking about nodes that are the size of disk blocks, right? And in the B+Tree terminology, we're going to call those pages. Okay, so one page of a B+Tree equals one page in a file system, one page on disk.
Yeah, I think thinking back to the LMDB show, we were talking about CPU caches and all sorts of things like that. Keeping the data that can be held in cache small, and that is what you're trying to do here, isn't it?
Yeah, that's why we only store keys in the interior pages and keep the actual data at the leaf. That means you can fit the maximum proportion of the key index in memory.
So you're not always having to go back to the file system to get the keys.
Right. Yeah, so when you're doing key lookups, they can all be in memory and very fast. And then when you actually get to the bottom of the tree and find the value that you want, then you might actually have to go out to disk, or some other slower storage. And that's the idealized case, right? But obviously, if you have a very small database, it could all be entirely in memory. And if you have a very large database, you could wind up with, portions of the interior index also pushed outside of memory.
And when we're talking about a B+Tree data structure, obviously that's a thing, but what does that thing look like on a computer or a hard disk?
Well, there's certainly a lot of leeway in how you construct it, at the bits and bytes level, but conceptually, it's not much different than the Btree, right? You have a root page, and the root page can have some number of pointers in it to children. And in this case, as I mentioned before, we no longer talk about it as an M-array tree. It's as many child pointers as will fit in a page. So it's not a fixed number. It's just you cram in as much as will fit before you have to overflow into a new page.
Okay. I'm still asking some really basic questions here, sorry. So is this data structure constructed from something on a file system or in a text file or something like that? How do you act? My question is coming from thinking about the data.mdb file, that LMDB creates in the first show we did together. What's inside that,
What's inside that? Well, that is just a sequence of pages, and each page, has pointers to other pages.
Okay. Yeah, I think I've got it now.
So in the textbooks, they will give you an example of a B+Tree where, all of the dimensions are fixed constants. It'll say you're going to create a B+Tree where every key is 8 bytes long and there are 8 keys per page. That's it, you're done. In the real world, keys can be various sizes, and because the sizes vary, that means the number of items that you can fit per page also varies. Right? So this is where, like a database engine like LMDB, departs from what the textbook tells you. Because the textbooks give you a very simplified version where there are no variables, and in reality you need to accommodate keys and records of varying sizes.
Yeah, real world data. Can you revisit and provide a simple description of a B+Tree?
Okay. So
if that's a thing.
Yeah, we'll start again. We have a root page, which can have, for example, a list of up to 8 pointers to children, right? And the children will be pages as well. So all of the pages are always the same size. So a branch page, again, points to more children. And then at the bottom of the tree, you have the leaf page, which points to actual data. And within each page of the root or the branch pages, you have the only thing that you store in those pages are keys. Keys and a pointer to the next level down, or the next thing that you're looking for. Does that make sense?
Yeah, I was just following it down my brain there. And B+Tree is a replacement for Btrees, or are they just different options?
Yeah, I would say it's a replacement. You find B+Trees being used everywhere, and Btrees not so much.
Okay, well, we don't really need to discuss trade-offs between them if everyone just uses B+Tree.
And we touched on it before. The main reason is that by keeping all of the data values at the bottom leaf pages, you get more keys in memory.
Which should be the smaller structure, shouldn't it? Smaller
That's
value.
Right.
And we've touched on RDBMSs, SQL databases that use them for primary keys and actually looking up the data that the keys point to as well. Can you think of any bigger products examples that use them? Or is it mainly just indexes?
Yeah, well, for example, SQLite, uses B+Trees for its indexes and for some of its tables as well. Obviously, OpenLDAP uses LMDB, so that's using B+Trees for indexes and for main data. The other popular databases, Postgres, is based on B+Trees. MariaDB or MySQL, they're actually using something called ISAM, completely different structure.
Yeah, that's right. I've seen that a few times. Okay, are there any places that you think could benefit from B+Trees where you don't see them? Or is it mainly in the database world?
I'm going to guess that, the database world has been around this for long enough. They know pretty well where they can leverage it. I would say in databases, they're already using it where it needs to be.
And have we touched upon the term height when we talk about leaf nodes?
Height. Well, height is just, a description of, how many levels of pages are in the tree,
Yeah, so how big the house of cards could be. How many?
Exactly, yeah. So if you have a tree that's just a single root page, then you've got a height of 1. There's nothing going on. If that root has just a bunch of leaf pages immediately under it, then it's got a height of 2. If it's got a root page and then some branch pages, and then immediately under that some leaf pages, then you've got a height of 3. So.
Okay. And do you have any tips on how to keep where you're working on in your head while you're dealing with these? Is it best to visualize things, write some sketches down, or do you just get used to them when you're doing it?
I suppose sketching on paper when you need to, but
or when you're using a library, does it matter? Do you need to?
It doesn't matter. When you're using the library, all you care about is here, insert this key, and here, find this key and give me this value. So you don't really care what the structure looks like underneath.
And you did your own B+Tree algorithm, didn't you?
For LMDB, yes.
Yeah. You obviously know the front end and the back end to that thing. Were there any lessons learned or tips or warnings to never do it yourself? If someone's thinking about it, what was your takeaways from actually doing the B+Tree algorithm yourself?
First of all, as I mentioned before, what you learn in the textbooks is only a very simplified version of what you're going to need in the real world. So if you want to write one of these yourself, be prepared for the textbooks to not tell you everything you need to know. And then you really need to have an extremely good reason to write this yourself, because at this point there are many libraries available, and you probably should just use one that exists off the shelf.
Yeah, I think it's the old profile and benchmark and look at stuff as and when. If there's an issue with something, isn't there?
Yeah.
Just have to trust that person or that company or team knows what they're doing.
Right. 10 years ago when I started writing LMDB, the things that we wanted it to have obviously did not exist off the shelf. So, that prompted me to write it. But I'd say it's hard today to find a use case that's not well covered by an existing library.
Yeah, I think people that are doing new things tend to reinvent things and forgot that there's probably something already there that was designed 20 years ago. They just haven't done enough research.
There's so much tendency to just reinvent.
And are you quite strict with yourself for trusting someone else has done it better than you? You've got a very strong reputation of speed and performance and getting the best out of things. Have you had to have words with yourself to not go down that route?
it's always the last resort. Always I search for something that exists that that would fit my needs before sitting down to write my own tool.
Yeah, I think that's good advice for any of the listeners. So I think we've touched on a couple of my questions already. I was going to ask why B+Trees are used for indexing and table indexes, and that's because I'll try and recap. They've got predictable times for searches and finding things, and they're very efficient at key value operations. So
yeah, they're actually optimal for searches. You'll always get the lower bound of search times. Yeah.
And okay, so with the B+Tree, is it complicated to get the data into it in the first place? How would you put a ton of data into a B+Tree structure?
Is it complicated? Well,
we're doing a whole show on it, so yeah, it's complicated.
There you go. Right. It's certainly, it's not as easy as the plain binary tree. It's not as easy as some of the other self-balancing trees. But one of the advantages, again, that it has, since it uses these relatively large pages, is, as you insert records into it, it has a fairly low rate of new allocations. Right? Every time you allocate a new page, it's good for 20, 30, 50 elements before that fills up and you're forced to allocate another page. So it's got pretty good efficiency in that respect as far as resource constraints.
Okay, that makes sense. I got a question from one of the other hosts here. How do we handle concurrency control in databases that use B+Tree?
There's a lot of different ways to handle that.
So that would be two processes trying to insert data with using the B+Tree library, and it hasn't quite finished putting that data in the right place. That's an easy way to understand it.
So this is one of those topics that, like I said, it has multiple different approaches. Okay. There's the very simple approach, which actually LMDB uses, which says we lock the entire tree for one writer, and we don't let go of it until that write is completely finished. So in that sense, we actually have no concurrency for writes. There's always only one writer at a time. And as I said, this is very simple, and
is that a decision that you've thought about changing at any point?
No. That's a decision that was reached after quite a bit of experience with other concurrency schemes.
And did you have to make a trade-off for that, or
make a statement? There is a trade-off in some ways. As you get to much larger databases, you might see that your overall write throughput could be slower than optimal. It really tends to depend on the write patterns. Another approach that, for example, Berkeley DB uses is to use lock coupling. That is, as you navigate down the tree from the root to the leaf where you need to insert data, you take locks on every page that you touch on the way down.
So then when the next write comes through, it might be trying to put it somewhere else, so it doesn't matter.
If the next write coming through is going to a different part of the tree, then it's possible for the two of them to proceed without interfering with each other.
And when you traverse the tree to find, or the algorithm is trying to figure out where to put the data in the tree, does it always need to can it go straight to that point, or does it have to do a similar search each time?
Generally, you always search from the root for every new operation.
Okay, so there's no quick way to say, this is the last place I put something. This new one is best placed here.
Well, actually, in LMDB, we do have an optimization that does that.
That's what I was thinking.
If you're putting in a couple of elements that are, that sort close to each other, or sort next to each other, LMDB will check that before it goes back to the root. So you have a cursor that points to where you're inserting data. When you insert a new record, it'll look at what the cursor is currently pointing at and see if it spans the space that the new record belongs to. And if it does, then it'll just stay on the current page. And if it doesn't, then it'll fall back to what it has to do. It'll go back to the root and search its way down.
And do you fall back to searching the whole route to the last leaf if that cursor breaks or something happens to it? Or do you just trust the fact that it points to the last place something was put?
Well, in LMDB, since there's no other writers interfering with it, then yeah, the cursor always points to what we expect.
So that's another good reason to have one writer.
Exactly, yeah. As I said, it simplifies so many things that, in my opinion, it wasn't worth the headaches of maintaining all the other state needed to do multi-page locking.
Yeah, it's like having a N+1 backup for the backup for the backup for the backup. How deep do you go?
How deep will you go? That's one of the problems with the approach in Berkeley DB is that you can get into lock conflicts very easily. Lock conflicts are not an exceptional, unusual condition. They're a routine occurrence in Berkeley DB when you have multiple writers. So every time you hit a lock conflict, one of the writers has to give up, release all its locks, and retry later.
And if I recall, sometimes if there was a crash, there'd be locks left.
Yeah, that's another aspect of things. So that's to do with writing in place versus LMDB's copy on write. But that's not quite related to the locking issues. So for concurrency management, that's one approach and that's the most common approach that Btrees use is the multi-page locks that Berkeley uses. There's another method which was relatively recent. I was reading about it back in 2009, called a B+Tree, where leaf nodes contain link pointers to their siblings. And by maintaining these link pointers, it actually allows you to do adds and deletes with high concurrency without as much lock overhead. So, this was a really interesting mechanism when I was reading about it. Unfortunately, at the time, it was very new research, and there were no working implementations that I could find anywhere on the web. And, the research paper that I read didn't provide me enough information that I could implement it myself. So I kind of set it aside. But it was a very promising paper at the time. I think in the years between then and now, there have been at least 2 implementations of it developed. Of course, while it solves some of the locking problems that we were just talking about, it doesn't solve the crash problem that you just mentioned, where if something crashes in the middle, then pages will be lost.
Yeah, and what was the last place written to and who was doing what?
Yeah.
Do you think there's, you just touched upon improvements that could be made with these types of data structures. Do you think in 2021 we've reached the predictable times for searching things and the software algorithms for these data structures, and we're now relying on hardware, or do you think there'll still be some major breakthroughs? Because I know you stay on top of all this stuff.
I see a lot of research into new algorithms that are supposed to be tuned specifically for persistent RAM or SSDs and thus and such. I find that the research I've read so far is not making any massive breakthroughs, and I don't from that trend I'm not expecting anything huge in the future. There's a lot of small scale refinements is really what it looks like, is what it amounts to.
And What do you think the future is for this type of data access?
Well, it's going to be more of the same. Today we have a multi-tiered memory hierarchy, right, where we talk about CPU caches and then RAM and then, quote, storage, which is disks or SSDs or whatever. In the future, we're going to have a couple different tiers of RAM. We'll have static RAM, dynamic RAM, we'll have persistent RAM. I would like to see further in the future, 100% persistent RAM and no more plain dynamic RAM. But, we're not going to get there yet. We're going to have this intermediate step first where we have dynamic RAM coexisting with persistent RAM. And so that will be another layer of the memory hierarchy. And it's just one more level of a pyramid.
But that won't change the page sizes that we're dealing with and the...
It doesn't have to. It doesn't have to.
So the same algorithms could still work, but because the access speeds are faster, it should still be predictably the same speed, or?
Yeah, a generic B+Tree algorithm will still provide optimal search performance as you layer these different memory technologies above each other. So that really doesn't need to change. Page sizes will increase, as you mentioned. 4 kilobyte pages are already a bit small for today's CPUs and disk subsystems. 16 kilobytes is more reasonable. 32K, 64K would probably be pushing it. But 4K is a bit too small.
And is that some size you have to pick in the B+Tree structure, or?
From the software side, you have to use what the hardware supports. So some CPUs today, for example, Apple's M1 processor, are now using 16 kilobyte pages. So that's the page size that your database should use as well.
So that means you can have a shallower tree.
Yes.
Because you're storing more value, or bigger values, or pointers to the values, rather.
More values per page, yeah.
Yeah. And which, again, speeds up getting things, because it's not so deep.
Right.
Okay.
Have you ever really been happy with your project management tool? Most are too simple for a growing engineering team to manage everything, or too complex for anyone to want to use them without constant prodding. Shortcut, formerly known as Clubhouse, is different though, because it's worse. Wait, no, we mean it's better. Shortcut is project management built specifically for software teams. It's fast, intuitive, flexible, powerful, and many other nice positive adjectives. Let's look at some highlights. Team-based workflows. Individual teams can use Shortcut's default workflows or customize them to match the way they work. Org-wide goals and roadmaps. The work in these workflows is automatically tied into larger company goals. It takes one click to move from a roadmap to a team's work to individual updates and vice versa. Tight VCS integrations. Whether you use GitHub, GitLab, or Bitbucket, Shortcut ties directly to them so that you can update progress from the command line. The rest of Shortcut is just as keyboard friendly, with their power bar allowing you to do virtually anything without touching your mouse. Throw that thing in the trash. Iterations planning. Set weekly priorities and then let Shortcut run the schedule for you with accompanying burn-down charts and other reporting. Give it a try at shortcut.com/SERadio. Again, that's shortcut.com/SERadio. Shortcut, again, formerly known as Clubhouse, because you shouldn't have to project manage your project management.
I'd like to start wrapping up. I think we've done a pretty good job on that. Let's just round off with the description of a B+Tree again, because we've digressed a little bit. So correct me on this. This is nabbed it off the internet. Just confirm for me. In the B+Tree, copies of the keys are stored in the internal nodes. The keys and records are stored in leaves. In addition, a leaf node may include a pointer to the next leaf node to speed sequential access. So are we calling the nodes pages there? Or
in that place, yes. The nodes are pages, yes.
Yeah. Why did it make sense to use the word page when everything else uses nodes for the previous data structures?
The word page is associated with virtual memory management and disk management.
And that's what we're trying to improve here.
That's
right. Laying the data on top of the disks or the SSDs. Excellent. Okay, so obviously selection of the correct data structures to use is extremely important to us. as software engineers and companies, but if there was one thing from this journey of an episode you would want our listeners to remember, what would you like that to be?
I would say most of the time for your data management needs, you're just going to need a B+Tree, and you can ignore anything else.
Perfect. And don't try and do it yourself. There should be a library for it.
Yeah.
Was there anything we missed that you'd like to mention? We did cover quite a lot.
We covered a lot of ground here, so I think we're good.
Excellent. So where can people find out more about your B+Tree I get it right, B+Tree work or what you're working on? Obviously, we've got your Twitter account that we'll link to. But I'm sure if people are interested, they can look into the source code of LMDB and get their head around how you've done B+Tree.
Sure, yeah. And also the lmdb.tech website has the formatted documentation online, so you can read through that there while you're browsing through the source code.
Thank you. I'll put that in the show notes. So this show personally has really helped me understand Btrees. Hopefully the listeners will come off a little bit better than when they started listening.
I hope they're less confused, yeah.
Yeah. So Howard, thank you for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.